Hi guys, this is topic 5.2, Introduction to Rate Law. Again, you are doing this most likely over Christmas break, so this is meant to help you out, meant to help you prepare for your AP exam. I know it's the Christmas break, but still got to do what we got to do. So the objective for this topic is to represent experimental data with a consistent rate law expression. Since a rate of reaction can only be determined experimentally, we're going to use the data to create a rate law. So a rate law describes how the rate of reaction is proportional to the concentration of each. So if you look at this example, it's a generic, not really a specific one clearly. It says D plus 2C produces AB. Notice, if we were just to analyze the actual rate law itself, what does it actually consist of? Notice how there are no products involved. So the concentration of this stuff, or the presence of that, does not really affect, so to speak. So you would describe this as having a zero order with respect to D, and first order with respect to C. That means that if the concentration of D is changed, it has no effect of the rate of reaction. If the concentration of C is changed, then that will change by the same factor, because this is in the first order. If I double C, my rate will double. If I quadruple C, my rate will quadruple as well. If you add up the coefficients, the sum of the coefficients, you're describing the overall rate law. So this reaction would be first order. 0 plus 1 is 1, so first order rate law in general. The coefficients itself have nothing to do with the rate law. It can only be discovered by experiments. So you're going to get data, and from there you need to figure out what that is. The constant K, which we're going to talk about in a second, differs for each reaction in the set of conditions. It is dependent on temperature, so this is probably something key we're going to have to think about. It is dependent on temperature. Okay, so that's you can almost bet that that will be considered a question on your exam. So this rate constant, you will be asked to solve this frequently and be able to provide the units. Okay. Just forgot to do the deal. So if it's a zero reaction, zero order, first 1, 2, 3, and then whatever it is. Usually it'll be between 0 and 3. So the units is molarity over time for zero reaction. First order, 1 over time, whatever the time is. So seconds, minutes, hours. 1 over molarity times time is a unit for second order reaction, and the third one will be 1 over molarity squared times time. So you may have to memorize this, unfortunately. May have to memorize this stuff. So example reactions. So you'll notice that there will be a bunch where, so, sorry, I had to step away. So if there's a weird pause, a weird transition in the speaking, I apologize. So you'll notice that they give you specific example reaction, well, not specific, but generic ones. Remember that the coefficients add up to the reaction order. So there's only 0, so it has to be 0. There's Ka, so the K times the concentration, with the concentration of A to the first order is only 1. You could have, for example, A with a superscript of 2, or you can have just an A and a B. So remember, you're adding up the coefficients that will give you the reaction order. But also you need to know these units. Comparing the initial rates, how do you figure it out? So you're looking at your initial rates, and the best way to do it is through a freaking example. This stuff with the change to variable, blah blah, don't worry about it. So let's look at an example. So you have A plus B produces 2C. So our initial concentrations of A and B are listed in our 3 different experiments. This is what they mean by experimental data, experimental whatever, right? So it has to be done experimentally. That's what they said. So concentration A, concentration B, we have 1 molar, 3 molar, and then 1, 2, and 1 for the B. And it tells you how fast or what is the rate of formation of C, molarity per second. So if you look at the data, we can see that there are 2 experiments with the same value for A and 2 experiments with the same value for B. So the concentration is held constant. So if we hold A constant, we can inspect the data. Okay? So that means the way the trick is, you have to look and see what's being held constant. So let's say that the first one, we can see that A is being held constant here in blue. So what we're actually going to do is compare the concentration of B, how that changes in respect to the concentration of the formation of C. So when A is constant, B is doubled. So it goes from 1 to 2. 1 to 2 for that one. And also the rate is doubled. So it goes like 1 times 2 gives me 2. And then 0.015 times 2 gives me 0.030. So the rate of change for both, it's the same. So that means that this is actually, concentration B is actually a first order reaction. If we look at C, so these two are held the same. So I'm going to look at experiment 1 and 3 and see how that compares. So from 1 to 3, so that means that to get to 3, it is tripled for my concentration of A. If I'm going to look at my formation of C, the rate is increased by a factor of 9. 0.015 times 9 is 0.135. So that means that, I have to be careful, this means that in order for me to get to 3 to 9, I have to square my 3. So that means my second reaction my concentration of A is, so it's, in terms of respect to A, it's considered a second order reaction. In terms of B, it's considered a first order reaction. So what does that exactly mean? So if we add our rate laws together, meaning second and first, so if we write it out as my rate equals K times the concentration of A squared times the concentration of B, the overall order is 3, or the third order. So that means we have to plug in our values now to solve for K. So we plug them in. Let's plug in, if we plug in our concentration of A times our concentration of B, we square the A. And then we just solve algebraically to get the value of K, whatever that is. Then from there we get our unit. So in reality, our value for K is 0.015, and my 0.015, my unit is 1 molar square times seconds. So looking at this, we can see that this looks a little weird, a little tricky. So you have more than one variable that changes. It's a little trickier to do it just by looking at it. You can compare 2 experiments like a weird, kind of weird ratio, I guess. Experiment 2 over experiment 1 equals rate 2 over rate 1. And then from there you figure out what is the actual rate law. If you look at the data, in the table we can see that there are no experiments with the same value for A, but there are 2 experiments with the same value for B. Let's start with finding the reaction order with respect to A. So if we compare experiment 1 and 2, that is held constant. So then now let's look, goes 1, so if it's held constant, concentration B, concentration A, it goes 1 to 4, and then 0.0016 to 0.064. That means that so if that's the case, that means that if it goes, so 1, so to get to there, it needs to be multiplied by 4. To get from 0.0016 to 0.0064, it's also multiplied by 4. So that makes that my reaction is going to be first order with respect to A. To figure out the reaction order for B, then you can use the equation above to do so. So what we're going to do is we're going to plug in our rate reactions, our initial rate of formation, 0.0064 molar per second over 0.0016 molar over second, and then kind of just plug in our numbers. When we do that, we're trying to find our new, what is our value for our order, so to speak. Because now we know that concentration A is by an order of 1, the first order. We're trying to solve for the order for the second one. When you do work out the math, the reaction is first order with respect to B as well. So therefore, your rate law is going to be rate equals K times A times B. So that means you're in a second order reaction. Plugging in your values from any of the trials would give you the value of K, which is shown here. The trick is to get this right, so then you can get this right. Consider the reaction carbon monoxide, CO plus NO3 produces NO2 plus CO2. Several experiments were conducted, and the data is shown below. Luckily for us, we have some that are constant, so that makes it way easy. So I'll take it. So what is the reaction with respect to CO? Let's look at the CO. So you have to look at the other ones that are constant. So we're going to cross this out. So that means we're going to focus on 2 and 3 for the first one. So to show your work, so to speak, we can tell that it looks like from 3 to 2, experiment 3, experiment 2, you multiply 0.0300 times 4 to get to 0.120. And then if you look at this over here, you also multiply by 4. So that means that for letter A, my reaction is a first order one. What is the order reaction with respect to NO3? So I'm going to knock these out, so to speak. So I'm going to look at, I'm going to erase that one. So I'm going to look at these two here, and then these two over here. This is going to be to find out my overall reaction for NO3, my second reactant. So to go from 0.360 to 0.270. So how do we do that? So to go from here to here, this is times 2, or divided by 2, I guess, if you want to look at it. 8.4 times 10 to the 3 times 10 to the negative 3 times 2 will give me the 1.68 times 10 to the negative 2. So that means this is also going to be a first order reaction. How do you get the overall reaction order? You add both. So this is now a second reaction, because first plus first is second. Sounds weird saying out loud. So then what's our rate law? The rate equals K times concentration of CO times the concentration of NO3. Different color now. What is the value for K with units? So what do we got to do? So we got to take our rate law, then plug in a set of numbers. So pick any set, make sure you're using, if it's experiment 1, you use all the numbers for experiment 1, etc. So I want to solve for K, so it's going to be the rate divided by the concentration of CO and then NO3 on the bottom. So the rate was, let's pick the first one, make it easy, 1.68 times 10 to the negative 2 molarity over seconds. Concentration of CO. So what is that? It's going to be 0.120 molar. And then the concentration of nitrogen trioxide, 0.720 molar. You do your math. So I'm going to divide my numbers, so I end up with 0.194. And then my units are molarity over seconds divided by molarity squared. In case I need to erase some stuff up here to create space. So to get our final answer, 0.194, then my unit will be 1 over seconds times molarity, all in the bottom. All right, so if you have any questions, please let me know so we can clarify. But if you have any questions, let me know. Thanks.